Yeah.
We're recording. So this is problem number 21 that Joy has asked about in the textbook, 11.221. They just give it to us in this long form, and we're going to use the ratio test. That's our go-to method for finding radius and intervals of convergence, and maybe it helps us figure out what to put into the ratio test if we can write it in sigma form. So I've just looked at the pattern here, see the factorials in the bottom, the powers in the numerator, and there is what we have. And so now we're going to use the ratio test. So Joy, you asked this problem. Do you have a specific question, or is just working through it? Is that okay for you?
I think it was just like getting to the point where we had the summation form, because when I looked at the example, it had like x plus 4 on the bottom, and I think that was just confusing me.
X plus 4?
Yeah, when I looked at the like example problem on Pearson.
Okay.
Or k plus 4 as the factorial on the bottom, and I think that was confusing me.
Yeah, so maybe they didn't start at 1 factorial, possibly?
Oh, okay.
Yeah. So, we just try to find a pattern here. For the problem in the book, it's pretty easy. The factorials, they start at 1 and they just go up. A tricky thing, and I'm not sure if, how often we run into it, and maybe never, is that how do we skip all the odd powers, right? The series they gave us, number 21, it only has even powers. Well, once you see how to do it, it's pretty easy. We're just going to double that k value, right? So when k equals 1, we get 2. When k equals 2, we get 4. So the 2k will allow us to. So it's kind of like in this power series, the coefficients of all the odd powers is 0. So they just drop out, and the only ones that survive are the even powers. So then we're going to do the ratio test. Let's do at least start it. It's a ratio test for absolute convergence. So when we use it, we ignore the alternating feature, and we take the absolute value of x to the 2 times the quantity k plus 1. We're plugging in k plus 1, right? And then we divide by the kth term. I've encouraged you to invert and multiply on the first step here. Okay. Can you see that okay? All right. And then some good things start happening. Like this k factorial cancels all of this one except k plus 1, right? K plus 1 factorial is equal to k plus 1 times k factorial. So this guy cancels out basically the factorial. Maybe I should do it in red so we can see the transition a little bit better. So this factorial cancels everything here except the k plus 1. And then, if we look at our powers of x, if you distribute this out, we have 2k plus 2, right? And here we have 2k, so the 2k's cancel. I'll do it in red again. All of these are right there. And it leaves those 2 extras. You see that? So we end up with the absolute value of x squared over k plus 1. And what's that limit?
0.
0. Okay, this is the ratio test. What does 0 mean?
It's less than 1, so the interval is negative infinity to infinity.
Yes, so it converts the limit did not depend upon the x value. It's 0 for all x. Most of the time, I don't know, often the limit that we get, there's an x in here, and then we have to figure out the values that make it less than 1. So this converges for all x, and you're exactly right, Joy. Am I too low on the board? I am. So r is infinity. We're in that case of our theorem, and the interval is minus infinity to infinity. Okay? Any questions about that, Nate?
Nope, that looks good for me. I haven't done the ratio test one in a while, so it was a good refresher.
Yeah, and this section 2, like I said, it's going to be our go-to method. There are some series occasionally where the root test will work, but in section 2, chapter 11, I don't think we would ever generally do anything else. There are some geometric series, and if we recognize it, we could use that, but we don't have to recognize it. The ratio test would work just fine on those as well. William.
Hello.
Good morning.
Good morning.
Thanks for checking in.
Yep.
So you can see on the board behind us, hopefully, that we worked through number 21. Joy, do you know the number it was on the assignment?
I think it was like the third problem.
Okay, so number 3 on the assignment this is from chapter 11, section 2. So, and we're recording this, William, so I won't say anything about it, and you can go back and watch it if you would like to take a closer look at number 21.
All right.
Does anyone have another question for me on this problem or any other? William, one of the things that made this a little bit tricky is that when we first saw it, they didn't write it in sigma form. And so to figure out, the formula for the ratio test, it really helped us to write it in sigma form. So we got to practice doing that. So William, do you have a question for us?
I was kind of curious on the comparison test. In the video, you showed us using 0 as one of the comparisons. I was wondering if you were, obviously you're able to do that, but I was wondering why you're able to do that.
Okay, so I think you're talking about the limit comparison test.
It might be. I thought it was the comparison test in the video where you squeeze it between 2 equations.
Oh. Yeah. I wonder if it was a series that had a sine or a cosine involved.
The equation was 3 over 2 plus e to the k.
Well, okay, tell me that one again.
3 over 2 plus e to the k, and it's infinity sigma k equals 0.
Okay, equals 0 to infinity.
Yep.
All right. So this is from chapter 10, not from chapter 11. We're not talking about power series. There's no x's in there. This is just a given series. And in chapter 10, remember what we care about is, does it converge or does it diverge? So I probably on the video, and Nathaniel, if you go and view that video that I talked with you about, I think this is maybe one of the examples I worked through there. Maybe that's why William's asking about it. So if the 2 weren't there, this would be super easy. It's a geometric series and we know exactly what to do, but the 2 is there. So we can't ignore it. We have to deal with it. But when I look at this thing and I think to myself, man, it looks kind of like the geometric series. We can all agree that as k goes to infinity, this exponential term blows up, and so this 2 is going to become less and less influential. In fact, I think it becomes negligible. But, you know, like I said, we can't ignore it. So I'm going to, and because we're adding 2, I know that this denominator is always bigger than that one. And because the denominator is bigger, it makes the fraction smaller. So I should have done something like this, William, and I'm not quite sure where the 0 that you're, maybe I do. Let's figure it out. All right, so e to the k is obviously less than 2 plus e to the k. I said obviously, do you agree with me?
Yep.
Yeah, can you see the board okay?
Yeah, I can see it fine.
Okay, good. And now if I reciprocate, okay, so maybe here's where the 0 came in. When I reciprocate, if I know they're both positive, then I know they flip places. You know, 2 is less than 3, but when you reciprocate, 1/3 is a smaller number, right? If one is positive, one's negative, then it's complicated, but everything is positive here, so no issues. If I flip them over, then this guy becomes the smallest one. And this guy, the biggest one. Okay with that?
Yep.
Yeah, and then let's multiply by 3. So everything here is positive. The terms of this are smaller than the corresponding terms of that one. All of them are. And we know because this is a geometric series, it converges. If I add up all of these, I get a finite number, and these are smaller, and they're all positive. So I'm going to get a smaller positive number. So by the comparison test, I'll abbreviate C period T period. Since this series converges, it's a geometric series. The series they gave us converges. So for 2 things, William, in order to establish this inequality right here, I had to know the numbers were positive. So that's why I cared about this. And then to use the comparison test, if you look at the fine print on the comparison test, we need positive terms there as well. So I'm just making sure that nothing turns negative here. Everything is positive, so I can handle the inequality, and then I can apply the comparison test. Okay?
Okay.
Yep. There are other tests we probably could use, but you know, we found one that works. I think the ratio test might work here, but that's okay. We found one that worked, and we used it. So this is the sort of thing you might be expected to do on the exam. Like, here's a series, find a test that will settle the issue, and run the test. You know, show me that you know the details, how to run the test. And that video where I review everything in chapter 10, I think is a pretty good summary. It turns out if you viewed that video, and William has, because this question came from it, we actually have 10 different ways to determine the behavior of a series, which may be too many. Like, if we only had 2 or 3, it'd be easier, like only 2 or 3 things to worry about. But with 10, we have a lot of power. So we'll go for the power at the expense of having to pay attention. I anticipate on the next exam, I mean, I talked with Nathaniel about the exam scheduled for next week. Haven't thought too much about how we're going to do this remotely, but if it's like an ordinary exam, I'd let you bring a 3x5 card. And so you need to be thinking about, how do I get the information about all of these tests onto my 3x5 card? Like, maybe some of them you need all of the details. And maybe some of them, you know, the ratio test, we're using it a lot. Maybe you can save space because you know the details there. But you need to think about that. and I'll let you think about what you need. Any other questions?
I am all good here. I got to run do my physics class. So thanks for the help. I'll probably be dropping back by Monday morning.
I'll be here. We'll see you, Nathaniel. Thanks for coming by.
Yep. See ya.
Yep.
Yeah, I have physics too.
You have physics as
But
well.
thanks for helping.
So we're recording right now.
Okay. Well, my question was actually about section 8 in chapter 10.
Okay.
It was the very last problem on the homework, and it was really strange because I manipulated the series correctly, and I got the correct answer, but I used the wrong test.
Well, what makes you think it was wrong?
So I decided to use the root test, and this is on problem 41.
Okay. 2 to the k. So the textbook problem is this.
Yeah,
Does that look similar to yours?
looks pretty similar.
All right. So 10.8, number 41.
Mm-hmm.
All right.
And the way I manipulated it was I divided the numerator and denominator by 2 to the k.
Okay. I think that's a pretty good idea. Which gets you 1
Yeah,
over, well, let's see, 3 halves to the k
yeah.
minus 1.
Mm-hmm.
And then you did the root test?
Yes. So my thought process was that behaves just like 1 over the quantity of 3 over 2 to the power of k, or that series.
Okay.
And then I used the root test on that ratio.
So you use the root test not on this series, but on a related series.
Yeah.
Yeah, so that's kind of a combination of
Yeah.
root test and the comparison test. You see,
So
you're
I do see. Is that a no-no? Is that
well, yeah, I think that's something we haven't talked about.
okay? Yeah.
So I love what you said at first. That is, it looks a lot like 1 over 3 halves to the k, which, by the way, you can simplify. So I'll just write similar to. If you take the 1 away, then you can just flip that over and you get 2/3 to the k, right? Maybe you did that.
Yes.
That's just a geometric series which converges.
Yeah.
Now,
That's what I found.
this is a super good example to illustrate why the limit comparison test is better than the comparison test in general. That is, okay, so let's forget about the root test for a minute. We'll just focus on this guy. You look at it and you say, man, it looks a lot like that guy. And we know that this guy converges. He's a geometric series. The trouble is these guys term by term are bigger than those, right? Because when you make the denominator smaller, you make the fraction bigger.
Mm-hmm.
So even though I think this series is going to have the same behavior as this one, the comparison test won't really settle the issue for me. Because, they could be bigger because they're converging to a bigger number, or they could be bigger term by term because it's going to infinity, right? We don't know. We can't tell. Just knowing that it's bigger. So let's try the limit comparison. Can you see this part of the board okay?
Yeah.
So we're going to do LC, limit comparison. the limit as k goes to infinity. The series we know we put on the bottom. The series we don't know
Mhm.
put on the top. It's kind of an ugly
Yeah.
and we won't panic. Let's do this. So did you watch the video where I wrote too low on the board and I kept saying, now you can see, and
Yeah.
eventually I got it worked out.
Yeah.
So, you know, I think it's easier if we go back to the form it was where we started.
Yeah.
Although let's see if we can make it work with yours. So we're going to take this guy, the numerator, which is 1 over 3/2 to the k. And then when we divide by this thing, we invert and multiply, right? So 1 over 3/3 to the k. Which is the limit as k goes to infinity. 1 over, if you distribute this, we get 1 minus 2/3 to the k. Right, those guys cancel out. 2/3 times 3/2.
Yes.
And so minus, this guy survives.
Yeah.
And now as k goes to infinity, what does 2/3 to the k do?
Goes to 0.
0. So what's the limit?
1.
1. So what does 1 mean for the limit comparison test?
It's less than. Then it converges.
It behaves the same.
Oh, really?
Yeah, it behaves the same. But what is our series that we chose? What does it do?
It converges.
Yeah, so it converges.
Right.
But what this means, we get a value here and it's a positive finite value. That means they behave the same. And then we go back and take a look, well, how did the series we chose, how did it behave? So you can prove convergence or divergence with the limit comparison.
Huh.
It all connects back to the series you chose to compare it with.
So, if we had a result of infinity, then that series would diverge.
Okay, do you have a book in front of you?
I'll pull one up.
Okay, or I can just read it to you.
All right. Yeah.
Yeah, so the comparison test, there are 3 possible outcomes. This is the one we really hope, like if we make the best choice possible for our comparison series, then most of the time we're going to get a positive finite value. Okay, that's kind of the way we hope it works. But sometimes we get 0 and sometimes we get infinity. It may be because we didn't make the best choice, or it may just be the nature of the series. And so the limit comparison, it has 2 other clauses. This is on page 685 of the book if you want to look later.
Yeah.
Remember, when we set up the limit over there, I said out loud, and you probably have observed this, and you know it, that is, we put the series whose behavior we know in the denominator.
Mm-hmm.
Okay, always do that. And then we get the second and third options. So on page 685, theorem 1015, the second one, the first case is this one, positive finite, and then everything is settled and we're done.
Yeah.
If we get 0 or infinity, then we have to kind of cross our fingers and hope it works out. The second case says if you get 0 and the series you chose converges, then the new one converges.
Yeah.
But if you get 0 and the chosen series diverges, we haven't settled the issue. We need another test, or we need to pick a different comparison. Sure.
Yeah.
And then part 3 says if you get infinity and the series you chose diverges, then the new one diverges. And again, if you get infinity but the chosen one converges, again, we've not settled anything, and we need to go back and take a fresh look.
Gotcha.
All right.
So they need to. Okay, so like in this case, the function on the bottom converges, and we've gotten a constant between 0 and infinity on the top. So therefore they converge together.
Okay, I'm not sure what you mean
Is
by
that right?
on the top.
Or in the numerator. My bad. Like the series whose behavior we're trying to determine.
Oh, okay. So you're talking about the guy on the top here, the unknown.
Right.
Series. Yeah. Yeah. So ask me your question again.
So because the series in the denominator, 2/3 to the k, that converges. And we've got a finite value from the test, then that means that the sum or the series in question, 2 to the k over 3 to the k minus 2 to the k, that must converge with it.
Yes.
That's perfect. Okay, and that converges to the same value because we got exactly 1.
No, not the same value.
Oh,
Remember in chapter 10, most of chapter 10, we're kind of giving up. But term by term, these guys are smaller than those guys because I'm sorry, bigger than those guys because we're making the denominator smaller. So we have proven that this series converges, and we can be assured that it converges to a larger number than this one because the terms, by one, they're all larger. We can actually find what this series converges to because it's geometric. And whatever number that is, we know this is going to converge to some bigger number, but we don't really know what it is.
yeah.
Find it at this point.
Gotcha.
Okay.
Yeah. All right. I think I'm getting it pretty well then,
Awesome. So I'll just say one more thing. I think you know this, but when we do the limit comparison and we get a 1, we're done, right? The test is successful. If we do the ratio test and we get a 1, then what?
Then it fails, correct?
Fails. We're not done, right? In fact,
yeah,
it didn't help us one bit, except that we can mark that test off the list.
It's got to be between 0 and 1, or no, it's going to be less than 1, right?
Less than 1, and then it converges.
Converge.
More than 1, it diverges. Those will settle the issue, but 1 doesn't.
Gotcha. Okay. Well, sweet. I think I'm good to go then. Gotta start studying for the. What's that?
What were you gonna say?
I was just gonna say I'm gonna get started studying for the exam.
All right. Yeah, and you did watch the chapter 10 review. That's a good place to go to. And on Monday, I'll give you more specific information.
Well, perfect. I might check that out again as well.